In this problem we have the circuit diagram. It's a bandpass filter and it's in series. So we're going to be looking at the formulas that start on approximately page 115, linked below the like button in the description. And here we're going to see that we have something that looks very similar to this. And we're actually given our H of S right here. And that's pretty important because it allows us to see that our actual circuit right here differs a little bit from the traditional basic one. And this is because, well, we have a resistor up here. So that means this resistor is going to be involved with this resistor over our inductor, when previously, if we were just to not have this resistor, it would just be R over L, so R naught over L. So that's important to note, and that's going to help us solve this problem. So first we want to find our F naught. When looking at this problem, we're dealing a lot with frequency. We can see that we're measuring things in hertz. That's important. When I initially did this, I made an error because in the previous problem that we did, it was done in rads per second. So mostly this was done in the actual omega. So instead of omega, we're looking more at frequency for this problem. The formula, the way we can find frequency, is that we are going to have our omega equal to the 2 pi times our f. So f is going to be equal to our omega divided by 2 pi. Now for f naught, what we need to do is look at the formulas. Again, in the description, link below the like button. We can see that it's derived for us a little bit here, and we are going to have that our omega naught is equal to the square roots of 1 divided by our L times C. So we're going to have the square root of 1 divided by our L, which is 312 times 10 to the negative 3, times our capacitor, which here is times 1.25 times 10 to the negative 12. That's what the P is for. P is for, I think, pico, and that represents a negative 12. And that is all in the denominator underneath this 1 that's in the square root. And this is going to be equal to approximately 1,601,282. Now we need to plug this into our frequency equation. So we're going to have frequency is equal to 1,601,282 divided by 2 divided by pi. And this is going to give us approximately 254,851 point, and we'll just have 9 here. Now it's in kilohertz, not just hertz. Currently it's in hertz. If we want it in kilohertz, we're going to have to move this over 3. And so our answer for F naught is going to be approximately 255 kilohertz. Now we need to find Q. If we look at the formulas, we can find this in the notes linked below the like button. And Q is going to be our omega over B. And we can simplify this. So this is one form. We'll have our omega over B, which is beta. And in simplifying this, we're going to have the square root of L divided by the C times our R squared. So in writing this in, we can say that we have the square root of 312 times 10 to the negative cubed. And this is divided by our 1.25 times 10 to the negative 12 for pico. And this is all being multiplied by our R. Now, our R, remember, we have this resistor and we have this resistor. So it's not like normal. We are going to have these two, and we're going to be focusing that right above our inductor. This is going to be our R, the two added together. So that's important to keep in mind here. So when we write this out, we're going to have 12.5 times 10 cubed plus the 50 times 10 cubed. And this is all going to be squared. And this is all being multiplied by the 1.25 times 10 to the negative 12 in the denominator, which is in the square root. And doing this huge calculation is just going to give us approximately 8. So our Q here is going to be 8. Now we need to find our F1, or FC1, sorry, and we need to find our FC2. Well, if we look in the notes, we have the following formulas for our omega C1 and our omega C2. We can use these, find the omegas, and then plug them in to our F. And if we do this, we are going to get our FC1 and FC2 to be respectively 239 kilohertz and then 271 kilohertz. Remember, our R here is going to be what we underlined in red right here. It's going to be the R0 plus RRN for this R, this R, this R, and this R. And that's going to give us our omega C1 and omega C2. Remember that our omega C1 has this negative in front, and our omega C2 is positive in front. And then we plug it into our frequency right here. Now that that's sorted, we can find our beta. Now, don't let this fool you, because if we solve for it like this, it's going to be in the omega form. So the omega form is going to be the R plus Ri divided by L. That will give us omega. Now, if we look at the notes, again linked below the like button, we can see that our beta is equal to the omega C2 minus omega C1. Now, we're dealing with kilohertz right here. This is super important to note. So we actually have to change this from our omega to be in frequency. So this is equal to FC2 minus FC1. And so we're not going to be looking at this. And we're basically going to have 271 minus 239. And this is going to give us approximately 32 kilohertz. And that's how you would go about looking at this problem.